You know, people always ask me, oh, what is the universe made of? And I tell them, well, that's a complicated question, but let me ask you something even stranger. What if everything, every atom, every star, every particle you've ever heard of, what if all of it is just one single electron and we're living inside the story of that one electron moving through time? Now I know what you're thinking. Feynman, that sounds completely insane. And you're right, it does sound insane. But that's the thing about physics. Nature doesn't care what sounds reasonable to you. Nature does what it does, and our job is to figure it out, even when the answer makes your head spin. Let me take you back. It was 1940. I was a young graduate student, and I got a phone call from my professor, John Wheeler. Wheeler was one of the most creative minds in physics and the man who later coined the term black hole. And he called me up with this idea. He said, Richard, I think I know why all electrons are identical. Now stop and think about that for a second. Every electron in the universe, and there are roughly 10 to the power of 80 of them, every single one has exactly the same mass, exactly the same charge, exactly the same properties. Not approximately the same, exactly the same, down to every measurable decimal place. Why should that be? If electrons were made in different places at different times through different processes, you'd expect some variation. You'd expect some to be slightly heavier, some slightly lighter. That's how it works with most things we build. No two things are truly identical. But electrons, they're perfect copies of each other, every single one. So Wheeler calls me and he says, Richard, what if they're the same because they literally are the same? What if there's only one electron in the entire universe and it's just moving through time in such a complicated way that it appears to be many? I want you to sit with that. One electron, one single particle. But instead of moving in a simple line from the past to the future, it weaves back and forth through time, crossing the same moments again and again. And every time it crosses your moment in time moving forward, you see it as an electron. And every time it crosses your moment in time moving backward, well, that's what we call a positron, the antimatter partner. And from where you're standing, looking at a slice of the universe at any given moment, you see this single thread woven so tightly back and forth over and over that it looks like an enormous number of separate particles. But it's one thread, one electron, tracing a path through all of space-time. Wheeler called this the one-electron universe. Now, I had to object. I mean, as beautiful as the idea was, I raised the obvious problem. If this were true, then for every electron moving forward in time, there should be an electron moving backward, a positron, which means there should be roughly equal numbers of electrons and positrons in the universe. But we look around and we see mostly electrons. We see very little antimatter anywhere. Where are all the positrons hiding? Wheeler had an answer, and his answer was inside protons. He suggested the positrons might be hidden somehow within the structure of normal matter. Now, that turns out not to be right. The physics doesn't quite work that way, and I knew it at the time. But here's what I find so fascinating. Just because the specific version of the idea doesn't hold up completely doesn't mean the underlying thinking is wrong. In fact, the framework that grew out of this conversation became one of the most important ideas in all of physics. Because embedded in Wheeler's one-electron idea is a profound truth. When a particle moves backward in time, it looks like it's antiparticle. That insight, that antiparticles are particles moving backward through time, that idea is real. That idea is part of quantum field theory. That idea is part of how we actually describe the universe today. So the one-electron universe as a literal fact, probably not. As a seed for a deeper understanding of space, time, and antimatter, absolutely. But let me push this further, because the idea of the universe being simpler than it appears, of all the complexity we see arising from something minimal, that thread runs through modern physics in a way that should genuinely astonish you. Let me talk to you about quantum field theory, because this is where things get really interesting. In quantum field theory, we don't think of particles as little balls sitting in empty space. We think of fields stretching across all of space-time, and particles are excitations of those fields. They are ripples. A photon is not a little pellet of light. It's a ripple in the electromagnetic field. An electron is not a tiny sphere of charge. It's an excitation in the electron field that permeates all of space. Now here's the thing about these fields. They're quantum mechanical. And that means even when a field has no particles in it, even in what we call the vacuum, it's not truly empty. It's fluctuating. There's energy in empty space. Particles pop in and out of existence, borrowing energy from the vacuum for brief moments, then paying it back Virtual particles, we call them. Not quite real, not quite unreal, more like the universe quietly humming to itself even when nothing is happening. And this vacuum, this quantum vacuum, it has structure, it has energy, and that energy has measurable consequences. The Casimir effect, where two metal plates held very close together in a vacuum are pushed toward each other by the pressure of the quantum fluctuations. That's real, that's been measured, that confirms that the vacuum is not nothing. So the universe, at its deepest level, is not made of particles and empty space, it's made of fields. And what we call particles are the moments when those fields do something notable. Now I want to come back to the question of identity, because the one electron idea was really a question about identity. Why do all these things look the same? And in quantum field theory, we have a beautiful answer. The reason all electrons are identical is because they are all excitations of the same field. The electron field is one thing spread across the universe. Every electron is not a separate object, it's a ripple in that one field. Of course, the ripples are identical. They're ripples in the same medium. They obey the same equations. They have the same properties because they come from the same source. And this is where things get philosophical, and I want to be careful here. I'm a physicist. I deal in equations and experiments. But physics has a way of bumping up against questions that philosophy has been wrestling with for centuries. When you say you are made of particles, electrons, protons, neutrons, what does that mean? Those particles are ripples in fields. The fields are mathematical structures that we use to describe reality. Are the fields themselves real? Is the mathematics real? Or is the mathematics just a map and the territory is something we haven't named yet? I'll be honest with you. I don't know. And I'm suspicious of people who are too confident that they do know. What I can tell you is that the mathematics works. It predicts things. It predicts the behavior of electrons to a precision of 1 part in a trillion. That's extraordinary. That's the most accurately tested theory in all of science. And if the mathematics works that well, you have to take seriously what it's telling you about the nature of reality. And what it's telling you is something like this. The universe, at its deepest level, is not made of things. It's made of relationships. It's made of patterns. The particle is not a thing. It's a pattern in a field. The field is not a thing. It's a mathematical structure that encodes how patterns can propagate and interact. And the whole elaborate story of matter and energy and force is the story of these patterns evolving through time, following equations that are themselves patterns of a kind, symmetrical, beautiful, astonishingly simple at the fundamental level. Now let me go one step further, because there's another idea that connects to all of this, and it comes from my own work on path integrals. When I was developing what's now called the path integral formulation of quantum mechanics, I was thinking about something Wheeler had taught me, that a particle doesn't take a single path from one point to another. In quantum mechanics, in some sense, it takes all paths simultaneously, every possible route, every possible trajectory, all at once. And what we observe, the classical path, the path that Newton would have predicted, emerges because all the other paths cancel out. They interfere with each other destructively. The crazy paths, the paths where the particle goes to the moon and back on the way to your detector, those paths exist, they contribute, but their contributions wash out because they're not in phase with each other. And what you're left with, what survives the cancellation, is the path of least action, the classical trajectory. So the universe is not taking the one path you see. The universe, in a quantum sense, explores all possibilities simultaneously. And what you experience as definite reality is the coherent result of all those explorations interfering with each other. This is not metaphor. This is how the equations work. This is how we calculate things. And it gives extraordinarily accurate answers. But think about what it implies. If the universe is constantly exploring all possibilities, if every quantum event is a branching, then in what sense is there one universe? Some physicists take this seriously and say there isn't. Every time a quantum event occurs, every possibility is realized somewhere. The wave function of the universe never collapses. It just keeps branching. And we are in one branch with no access to the others, but the others are just as real. That's the many worlds interpretation. I'm not going to tell you it's right. I'm not going to tell you it's wrong. I'll tell you it's one honest way of taking the mathematics seriously without adding any extra assumptions. But here's what all of these ideas have in common: the one electron universe, the quantum field theory perspective, the path integral, the many worlds interpretation. They all point towards something that should make you deeply humble. The universe is stranger than our intuitions. The universe is more connected than it looks. The divisions we draw between things, this particle and that particle, this moment and that moment, this possibility and that possibility, those divisions may be less fundamental than we assume. The separateness we experience might be a feature of the particular slice of reality we're embedded in, not a feature of reality at its deepest level. I find that beautiful. I find it thrilling. It doesn't make me feel small. It makes me feel like I'm part of something unimaginably vast and strange and elegant. Now, I want to come back to the specific question, could the universe be one particle? And I want to be careful about what we mean. In the literal sense, Wheeler proposed, one electron tracing a world line back and forth through time, probably not, for the reasons I mentioned. The antimatter problem is real. The numbers don't work out the way that idea requires. But in a deeper sense, in the sense that everything is an excitation of one set of fields, that all particles of the same type are genuinely identical because they're expressions of the same underlying mathematical structure, that the separateness of things is not as absolute as it appears, and in that sense, yes, there is something to the idea. The universe is not made of billions of separate little things bumping into each other. The universe is made of fields, and those fields are interwoven. Quantum entanglement tells you this directly. When two particles become entangled, measuring one instantaneously determines something about the other, no matter how far apart they are. Not because a signal traveled between them, nothing traveled. It's because they're not truly separate. They're correlated parts of one quantum state. The boundary between them is conventional, not absolute. Einstein hated this. He called it spooky action at a distance. He didn't believe it, but we've tested it. We've tested it over and over with increasing precision. And every test confirms that the universe really does work this way. Entanglement is real. Non-locality is real. The separateness we perceive is not the whole story. So what is the universe made of? I think the honest answer is, we don't fully know. We have extraordinarily successful mathematical descriptions. We have quantum field theory, which is the most precisely tested framework in the history of science. We have general relativity, which describes gravity and the large-scale structure of space-time with breathtaking accuracy. But these two frameworks don't fit together yet, and that tells us we're missing something. String theory attempts to unify them. Loop quantum gravity attempts it differently. There are other approaches. None of them are confirmed yet. None of them are wrong yet, at least not in any region where we can currently test them. The frontier is genuinely open, but here's what I think we can say. The frontier keeps moving in one direction. The deeper we go, the more unified things look. The more we discover that things we thought were separate are actually related. Forces that looked different turn out to be aspects of one force. Particles that look different turn out to be excitations of the same field, or related by a symmetry we hadn't noticed. The history of physics is a history of unification, of finding that the world is simpler and more connected at depth than it appears at the surface. And Wheeler's crazy idea that one particle might be doing everything is a kind of extreme version of that instinct toward unification. It's a physicist asking, what if we've been counting wrong? What if the multiplicity we see isn't fundamental? I think that instinct is right, even if the specific idea needs adjusting. The universe probably isn't one electron in the literal sense, but it might be something far more unified than our everyday experience suggests. The multiplicity of things might be not an illusion exactly, but a particular perspective, a view from inside a very small corner of a very large, very strange, very beautiful structure. And if I had to bet, and I am someone who likes to bet, I'd bet that when we finally do find the theory that unifies quantum mechanics and gravity, when we finally see the thing that underlies both, it will make the universe look even more unified. Even more like one thing, exploring all its own possibilities, generating the rich complexity we see around us from a foundation that is spare and elegant and surprising. That's what physics keeps doing to us. Every time we think we understand the level we're at, we find a deeper level. And at that deeper level, things are simpler again. I expect that to continue. I expect the universe to keep humbling us and delighting us in equal measure. The one-electron universe, it might not be literally true, but as a way of asking the right question, as a way of looking at all this complexity and asking, is this really many separate things, or is it one thing doing something very complicated? As a question, I think it's exactly right. And the fact that a phone call between a professor and his student in 1940 could plant a seed that's still growing, still touching the edges of what we understand about reality, that's not just beautiful physics. That's why I love physics. Because the questions are so much bigger than the answers we have, and there's always more to find.